Cảm ơn Claire.
Kia đã xảy rồi. Không phải nè, tôi không phải này à. Tôi không ăn nói với tôi đã thấy rồi mà có.
Okay. Everyone, we're all set. I just got my second COVID vaccine, Moderna vaccine yesterday, and I feel like I was hit by a truck. So I hear that it only lasts about 24 hours.
Don't touch my hand.
Right,
Don't touch
are there any questions before we get started? So where we left off, we were talking about the theory of the Big Bang. This is cosmology. The universe as we know it, they think it may be infinite in extent. We'll talk about this, but nonetheless, it's been expanding. It started out infinite, and it's still infinite, perhaps. But nonetheless, it's been expanding for 14 billion years, and we call this the age of the universe. Started out in a very hot, dense state, and since then it's been expanding and cooling off. And things happen when it expands and cools off.
Lock the door, not that.
Stars, or galaxies. And so we're going to be talking today about some of these things that happen.
Wash your hands.
About what happened right after the Big Bang. For example, remember stars and the medium between stars is mostly hydrogen and helium. That came from the Big Bang. Since then, the stars have been turning out through fusion heavier elements like carbon, stuff we're made out of. But initially, there was the simplest elements that came from the Big Bang. So what's the theory about how that came to be? Well, initially, the universe was very hot. And as it cooled off, you could snap together the simplest building blocks. So we'll talk about that today. One of the big ingredients to this theory is that the observation that the universe seems to be expanding, right? This is one of the key pieces of evidence that tells us the age of the universe. The fact that it's expanding means that if you roll back time, it was initially hot and dense, right? And this is called Hubble's law. And so as a quick reminder, if you look at distant galaxies, the further away you look, so that's the x-axis, distance, you look, the faster those galaxies are moving away from us. Very interesting. The further something is from us, the faster it's moving away from us. It's called Hubble's law. And as we'll discuss today, that tells us that the universe as a whole seems to be expanding.
Give me the wood chair.
And you see that this law, due to Hubble, is extremely accurate. You go
Right there.
million parsecs, then things on average are moving, a few thousand kilometers per second away from us. You go 200 megaparsecs, it's like 10,000, and so on. It just keeps going up along a straight line, further away from us. And the way we can tell how fast it's moving away from us is
computer in the room.
galaxies look redder faster than moving. So here's a kind of a cartoon of the same observation due to Hubble. He was using Cepheid variables to determine distances. That way he could get the x-axis, right? These numbers here using Cepheid variables, that's a type of star where we could know its intrinsic brightness through how fast it kind of oscillates in brightness. But then we've also used supernovae, which all have about the same intrinsic brightness, the same luminosity. So we can tell how far away that supernova is, even if it's in a distant galaxy, by how bright it appears to be. It allows us to infer how far it actually is. The modern value of this Hubble parameter, that's the slope of this line, is 70 kilometers per second per million parsecs. Every million parsecs away, that's about 3 million light years, you add an additional speed of a galaxy moving away of about 70 kilometers per second. Now, there's a number of ways of trying to understand this observation, or to convey why this means that the universe must be expanding. And you can think of it in 1, 2, or 3 dimensions. Now, the real world is 3 dimensions, but sometimes it's maybe even simplest to just, if you take a rubber band and mark off with a, before it's stretched, mark off using a Sharpie, some little dots, those are like galaxies, and then you stretch the rubber band, the galaxies move apart, right? And if you pay attention, you'll see that the nearby galaxies are moving apart slowly, but the galaxies that are further apart are moving apart fast. In fact, they're moving exactly in proportion to their distance from each other. So that's a nice analogy of exactly what's happening in the real world. That the space itself is expanding, and as a result, galaxies are moving away from each other. Another way of thinking about it is like the surface of an inflating balloon. You can do the same idea of marking out little dots with a Sharpie on the surface of a balloon. And then when you blow up the balloon, those dots move away from each other. And in fact, the further the dots are from each other, the faster they are moving away from each other. Now, the real world is in 3 dimensions. So maybe the best analogy is if you let a cake, like say a raisin cake. So you can think of the raisins representing the galaxies. You put it in the oven and it expands, right? You watch a cake as it rises in the oven. Well, the distance between each raisin gets further apart. And the farther apart raisins are, the faster they're moving away from each other. Are there any questions about this idea about understanding Hubble's law in the context of an expanding universe? You can think of the space itself, right? Just like the dough that's expanding is causing the galaxies to move apart. Now, the theory surrounding the expansion of the universe is called Robertson-Walker cosmology. And this is the Friedmann equation. And what it tells you is H, the Hubble parameter. In other words, how quickly is the universe expanding? And it relates that to 2 things. It relates it, so these are some constants here. It relates it to rho, that stands for the energy density in the universe. So that includes how much light there is, how much matter there is. As we'll see, it has to do also with how curved the universe is. So the density of the universe tends to want to pull the universe back in. It also depends on the size of the universe. And this K parameter controls, it can either be +1, 0, or -1. If it's 0, that means the universe is flat. We talked before about the universe can be curved in different ways. You can imagine it's like the surface of a balloon. That corresponds to what we call a closed universe, where this K constant is +1. In a closed universe, for example, if you make a triangle, the angles add up to more than 180 degrees. It's what we call a non-Euclidean geometry. We could also potentially live in an open universe, we call it, with K-1 in this equation, corresponding to, for example, if you were to draw a triangle, the angles would add up to less than 180 degrees. And these are the 3 possibilities for what the geometry of the universe could be. It could be closed, flat, or open. And depending on the amount of stuff in the universe, rho, depending on the size of the universe, that tells us how fast the universe is expanding. Now, at the end of the day, what we're kind of interested in here is, well, does that mean the universe is, we know the universe is expanding. Well, is that expansion slowing? Which is what's shown here. The universe is expanding, but it's slowing down. Maybe it'll even collapse again. Or is the universe accelerating its expansion? Is it just going to are the galaxies going to keep flying apart faster and faster and faster? So that's something we're going to discuss today. Another thing that we want to discuss is what's called nucleosynthesis. This is the formation of the elements. Before there were stars, we call this primordial nucleosynthesis, right? So look, here's a periodic table describing the origin of the elements. And we talked about how the heavier elements are formed in stars, right? Carbon, right? Iron, formed in stars, okay? But there's what happened before stars, right? How did you get the hydrogen and helium to go into stars? Well, the simplest elements, mostly hydrogen and helium, but also some lithium and beryllium, formed in what we call primordial nucleosynthesis. That's before stars. In the early seconds after the Big Bang, things expanded and cooled off to the point that protons and neutrons could snap together, forming the simplest elements. And this Big Bang theory allows us to calculate what we should expect for the amount of hydrogen and helium and other primordial, we say, elements, that is, elements before stars came along. Now, there's a famous paper from 1948 explaining how primordial nucleosynthesis should work. And it has a funny set of authors, alpha, beta, gamma. Those are the first three letters of the Greek alphabet, alpha, beta, gamma. Alpha and beta are two famous physicists. Gamow, which is similar to gamma, is also a famous physicist. So they kind of funnily have authors, alpha, beta, gamma. And the basic story goes like this. So imagine the universe started out extremely hot and dense, so hot that you couldn't form elements, right? Everything is vibrating. That's what temperature is. Remember, things are banging around so fast they can't slow down to snap together to form elements. We measure the temperature in what are called electron volts. So maybe 1/100,000th of a second after the Big Bang, things are at 200 million electron volts. It's very hot. At that point, things cool off enough for protons and neutrons to form. These are the building blocks of nuclei. By the time the universe expands and cools down about a factor of 200 to 1 million electron volts, it's been about a second has elapsed. And now we stop producing neutrons and protons. So we say they freeze out, meaning we're left with just neutrons and protons, and there's about 1 neutron for every 6 protons. And this fixes, almost, we'll get to one more point, but this fixes the basic building blocks of nuclei going forward. In the next few minutes, the universe continues to cool. And the thing about neutrons is if they're not bound into a nucleus, they decay. So actually neutrons, we talked about this process before, it's called beta decay. Neutrons decay into protons. So actually in the first few minutes while you're just having these protons and neutrons floating around, some of the neutrons are decaying into protons. So actually this theory predicts that you end up having 7 protons for every 1 neutron. And this is really important. This kind of fixes, like I said, the basic building blocks of how much hydrogen and helium and lithium and stuff form later. We'll go through that. Now, by about 3 minutes, the universe is cooled enough that you can snap together a proton and a neutron to form deuterium. So this is one of the basic elements, right? So remember, you have hydrogen and helium, but you also have other isotopes of hydrogen. You have deuterium is a main other isotope of hydrogen. That has 2 protons. Proton and a neutron. Finally, there's the theory of how you get little bits of helium-3. We'll talk about helium-4 in a second. Little bits of lithium due to just collisions that happen in the first few minutes after the Big Bang. While space is still small enough for things to be colliding and combining in very space. But then the universe continues to expand and cool, and eventually you're left with just this interstellar medium with some amount of hydrogen, some amount of helium, and so on. It is called Big Bang nucleosynthesis. And it's something we consider one of the major successes of this idea of the Big Bang, because it actually works, as we'll see. Yeah, so let's do this calculation. So I said that there are about 7 this theory tells us there should be 7 protons for every 1 neutron after the Big Bang. So that means 14 protons for every 2 neutrons. Well, what are the simplest building blocks that these form? Well, you can either have lone protons, which is what hydrogen is, lone protons combined with electrons to form neutral atoms. So if you have 14 protons for every 2 neutrons, you can form 12 protons, and then combine 2 of those protons with 2 neutrons to form 1 helium nucleus, because a helium nucleus has 2 protons and 2 neutrons. So you actually predict you should get 12 parts hydrogen for 1 part helium. And if you do the math for the mass, right, this you have 4 to 12, in other words, 25% helium by mass to 75% hydrogen by mass. And this is what we see. This is what we see in solar systems and the interstellar medium. We see about 25% helium by mass, 75% hydrogen. So this is a major success of this theory of Big Bang nucleosynthesis. So I'll give you a poll question in a second, but as a warm-up, what do we mean by primordial helium? What does that mean, primordial helium? This is the helium created by the Big Bang itself, before stars were born and began to form some additional helium through fusing hydrogen. It's primordial. It's before stars, helium created by the Big Bang itself. And what did we say after the Big Bang nucleosynthesis? What fraction of normal matter was helium? So this will be a whole question. What fraction by mass of normal matter was helium?
Yeah, it's 25. Wait, 25?
Okay, I'll give you 10 more seconds. Okay, I'm gonna end it. And very good, most people got the correct answer. This was 25% by mass, 75% hydrogen, 25%. Any questions about Big Bang nucleosynthesis? So I do want to just point out that it's a little bit more complicated than this, because besides hydrogen and helium, there's little bits of other stuff. I mentioned deuterium. So this is the whole reaction network that you talk about. There's neutrons and protons, and they can combine in various ways. Remember, there's about 7 neutrons for every 1 proton. You can form a little bit of deuterium, which is 1 proton, 1 neutron. You can form a little tritium, which is another form of hydrogen, 1 proton, 2 neutrons. You can form a little bit of helium-3, which is 2 protons, 1 neutron. But mostly you're forming hydrogen and then helium-4. That's 2 protons and 2 neutrons. And then you also form little bits of lithium-6 and beryllium-7 and lithium-7. And these are all the primordial elements.
Can you just stop that one?
Totally negligible amounts of, say, carbon were formed in the Big Bang. And almost entirely it's hydrogen and helium. Everything else was formed in stuff. Or through, as we discussed, through the death of stars. Okay, so Big Bang theory accurately predicts the relative abundance of hydrogen, about 75%, helium-4, about 25%, and it also predicts like tiny fraction of deuterium, helium-2, is at the tiny fraction of percent before the first stars were formed. And these abundances are sensitive, like in our theory, they depend on how much light there was. We call this the baryon to photon ratio. And so all of these results agree with what we'll talk about in a moment, the cosmic microwave background, which is the light we still see from the Big Bang. This is all consistent with the amount of light for every baryon. The number of photons for every one of these protons or neutrons is about 10 billion. Okay, that's what this number means. So there are about 10 billion particles of light for every proton or neutron. We'll come back to this. This will tell us something interesting. Okay. And so I just want to prelude that when you talk about Big Bang nucleosynthesis, we're not just talking about hydrogen and helium. There's also light, right? Of course, there's light. And we are about to talk about the cosmic microwave background, which is the light still reaching us from the Big Bang. And what we'll learn as we go forward is what the universe is made out of. Okay, now we just talked about hydrogen and helium. It turns out that's right. That makes up the majority of what we call ordinary matter. Okay, most of it is actually in the interstellar medium, as we've talked about, outside stars. So if we add up all the stuff in the universe, about 0.6%, less than a percent, is what's in stars. It's mostly hydrogen and helium. Then outside stars is about 3.8%, also hydrogen and helium. So in total, ordinary matter makes up about 4.6% of all the stuff in the universe. Now, my research specialty is what's called dark matter. We'll have a whole lecture on that. So one thing we'll learn that comes out of what we're going to talk about is that most of the matter in the universe, we can't see directly. It's very hard to see. We already know about dark matter particles that we can detect called neutrinos. I told you about neutrinos. We have these enormous tanks underground that can detect some tiny fraction of them. They're very, very ghostly. But there's other types of particles we think that are very much like that, that make up even more matter. And collectively, we call this dark matter. Then there's dark energy, which is a little bit different from dark matter. They shouldn't be confused. Dark energy is the energy in the fabric of space itself. Okay? And it's something that can cause the fabric of space to want to expand. Okay, so we're going to talk about this in a moment. As we also talk about the expansion of the universe. It depends on how much matter is in the universe. Matter gravitates to pull things in. The energy in space itself actually wants to push space out. So there's a competition of these two things of determining whether the universe wants to expand or contract. So one of the major pieces of evidence in Big Bang cosmology is the cosmic microwave background. This is the fact that we can actually still see light reaching us from the Big Bang. How is that possible? The Big Bang happened 14 billion years ago. Well, it's because the universe, as far as we can tell, is infinite. And it takes light time to reach us. So if we look far enough away, there's still light traveling 14 billion light years from really far away from the Big Bang that's constantly reaching. Remember that everything that has some temperature radiates light. We talked about how humans we're constantly radiating infrared light. Put a piece of metal in a flame, eventually it'll go red. You make it hotter, it'll start to glow orange and yellow, and eventually it'll start glowing, adding blue and green and violet. All together, that'll make it look white. White is all the colors of the rainbow together. So when we talk about black body radiation, remember, the hotter something is, the more light it's emitting, and the color gets bluer and bluer the hotter it is. Now, the Big Bang had a temperature at various points. Remember, as it expanded, the universe started out very hot and dense, and it kept cooling off. Also, if the universe was expanding, whatever the temperature was of the universe that we're looking at, if we're still receiving light from the Big Bang, now the Big Bang was very hot, but the universe has expanded in that 14 billion, stretching out the light waves so that they are redshift. So what it turns out is that the light we're seeing from the Big Bang was a time when the universe was red hot, but due to the expansion of the space, the Doppler shift, the stretching of light, to longer wavelengths. That same light that did correspond to the universe being about 3,000 degrees Kelvin. Now it's microwaves. Microwaves, the same stuff that's in your microwave oven, which is emitted by things that are very cold. Okay? This was first detected in 1965. Penzias and Wilson were working at Bell Labs with this antenna that looks kind of like a horn shown here to detect radio waves bouncing off of these balloon satellites. But they kept seeing this noise. Any direction they looked, they kept receiving microwave signals. We now understand this is any direction, anywhere you look. We're constantly bathed in microwaves from the Big Bang itself. You can't escape it because anywhere you look, there's light still reaching us from the Big Bang, and we can study it in great detail. So we say it's expansion redshifted, meaning it was initially about 3,000 degrees Kelvin. Okay. That corresponds to about 370,000 years after the Big Bang. The reason why we can't see any further back than that is because this is the point where atoms combine to become neutral atoms so that light could escape. Light could then flow through to reach us. And the universe cooled down to the point where neutral atoms could form, about 370,000 years after the Big Bang. And since then, the light's been traveling.
Can you wear pants?
Until it reaches us.
Can you
and
cool?
the light now, even though it was kind of red hot, corresponds to 3,000 degrees Kelvin, it now corresponds to about 3 degrees Kelvin. I think it's the sort of waves that are light waves that are emitted by something that's actually really cold. 3 degrees Kelvin is really, really cold. That corresponds to a wavelength of about 2 millimeters. In order to study this in detail, we first, in order to really first understand this well, we sent up satellites. The first major one was called the Cosmic Background Explorer, COBE. Here, it was set up around 1990. Two other big ones were WMAP, Wilkinson Microwave Anisotropy Probe. That was launched in 2001, and then Planck Surveyor by the European Space Agency in 2013. And here's what we saw. So these satellites that went up were able to measure the spectrum. As you look across the sky, you see light from the Big Bang. And they were able to measure with more and more accuracy tiny little fluctuations in the temperature of the Big Bang as you look across the sky at smaller and smaller angles. So you can see that's kind of fuzzy for COBE, WMAP. Then you get to Planck and you're seeing these tiny little differences as you look across the sky. Some regions are slightly warmer or slightly cooler. And this has a very deep significance. This is the sort of thing that in the very early universe seeded the formation of galaxies and stars themselves. The regions that were a little cooler allowed stuff to condense and form galaxies. The regions that were a little hotter, remember, stuff expands where it's hot. And so you don't form galaxies there. And there's a whole lot of information that you can get out of these, out of studying this spectrum. Here's, if you look at the COBE microwave results from around 1990, first thing you see, if you look without doing any analysis on your data, you'll see something like this. That is, one part of the sky will be kind of brighter than the other, or redder than the other. And the reason why, of course, is because the Earth is spinning. So if you look in the direction that you're spinning, you're moving in that direction. So things are blue shifted in that direction. If you look the opposite direction, it looks like things are moving away from you. Things are red shifted. So you have to subtract that out. And when you do, you see these tiny little fluctuations in the temperature as you look in different directions across the sky. We've gotten more and more detailed as we've gone to WMAP and then Planck. So Planck can measure the cosmic microwave background, light from the Big Bang, as you look across the sky to see temperature fluctuations from the Big Bang of less than 1 part.
Don't break the chair, man.
100,000 to that precision. And again, these are the tiny temperature fluctuations very early on in the universe that we're able to seed the formation of things like stars and galaxies. The cooler regions are where stuff can condense to form stars and galaxies. The warmer regions are too hot to do that because stuff expands. Furthermore, our theory of Big Bang cosmology can actually make really, really precise predictions about the degree of fluctuations as a function of nature. So this is a kind of might seem like a complicated plot, but I'll try to do my best to explain it to you because it's of deep significance. On the x-axis is angular scale. That is, if you look at large pieces of the sky, that's large angles to the left. And if you look at really fine angles in the sky, that's moving to the right, to smaller angles. And as you look at larger angles or smaller angles, you'll see different amounts of temperature fluctuations. And essentially what you're seeing is the vibrations of the universe just after the Big Bang. Why were there vibrations? Things were ringing like bells. Why? Because things with gravity want to contract, but when you contract, you get hot. Things want to push back out. So there's a competition between things that want to pull in and then get hot and want to push back out. And so what we see are these peaks and valleys corresponding to essentially ringing vibrations in the early universe. And these allow us to predict extremely precisely how much matter, how much dark matter, things of great significance to our understanding of the universe just from looking at this plot. And the theoretical prediction is shown in green, and the experimental data is shown in red. And what you see is an incredible matching between theory and experiment here. Not only does it tell you how much matter, how much dark matter there is, how much dark energy, it tells you about the geometry of the universe. If the universe is open or flat, the fluctuations are at smaller scales compared to if it's closed. So here's examples of what you'll see. What the cosmic microwave background seems to show is that, as best we can tell, the universe is flat. It could have been open, it could have been closed, but it seems to be flat. Any questions so far? Now, something that's interesting that us physicists ought to think about is, well, if things were really hot and dense during the Big Bang, just a fraction of a second after the Big Bang, particles were colliding with great energy. We call this high energy physics. And it's like a big particle collider. Right now, we're trying to collide particles like the Large Hadron Collider to try to discover new forces, new particles. But during the Big Bang, in the tiny fraction after the Big Bang, it was doing that with way higher energies than we can ever hope to do on Earth. So there's a great deal of study about what happened during that time. So let's discuss a little bit about what we do know. We understand that there's 4 forces in nature. Another way of thinking about a force is it's an interaction. Some way 2 things can interact. There's the electromagnetic interaction. If you have a positive charge and negative charge, they'll attract. If you have a positive charge and a positive charge, they'll repel. Negative charge and a negative charge, they'll repel. That's actually the interaction that governs most of the chemistry that goes on in our bodies or in our normal objects in our house and daily life. How what holds atoms together. There's also the weak interaction. This causes certain types of radioactive decay. It's pretty weak. It's not the sort of thing that's super important in our daily lives. Then there's the strong interaction. This is what holds nuclei inside atoms together. It also binds what we call quarks together to form the protons and neutrons. It has to be strong, remember, because in a nucleus, if you have a bunch of protons want to repel each other due to the electromagnetic interaction. So you have to be strong in order to still hold the nucleus together. Finally, there's a fourth force, gravity. And gravity is very, very weak, right? It's so weak that you only notice it if you have a whole planet with stuff all pulling inward, right? So gravity is an attractive force between anytime you have a whole lot of matter. Now, in high energy physics, we've understood actually how to predict all of this, well, electromagnetic weak and strong interactions. This is actually an incredibly beautiful story where while you don't have the math of having learned quantum mechanics to maybe appreciate it at the technical level, maybe I can explain enough to give you some appreciation of what physics has been able to uncover. And that is that symmetry governs, as best we can tell, most of physics. Let me give you a few examples. As best we can tell, if you do an experiment on, say, a table, and you get some result, if you move that experiment, say shift it to the left or to the right by a few meters, you get the same result. Physics is invariant or symmetric with respect to position. It doesn't matter whether you do something here or here or here, the physics is the same. Mathematically, Emmy Noether proved in 1918 that means that momentum is conserved. That's where momentum comes from. Momentum is the thing that's conserved. It doesn't change because of that symmetry. What about energy? Energy is similar. It turns out that if you do an experiment at noon and you do the same experiment at 2 p.m., you get the same result. We call that time translation. It doesn't matter what time you do an experiment. Physics is the same. It turns out that the thing that's conserved corresponding to that we call energy. That's where energy comes from. That's the thing that is conserved due to time symmetry. Similarly, angular momentum. We talked about as an ice skater, you twirl faster. That's angular momentum conservation. That's due to the fact that if you take an experiment and you rotate it, you get the same result. The angle of rotation doesn't matter. It's a symmetry. So this is a beautiful and deep result in physics. Symmetries give us laws of physics. And now this is getting a little bit more mathematical and abstract, but just to give you a taste, we can predict the existence of electricity and magnetism, and predict the weak interactions, predict the strong interactions, all as types of symmetry. They have these fancy names: U1 symmetry, SU2 symmetry, and SU3 symmetry. In some sense, the three simplest symmetries, in addition to spatial, time, and rotation, give rise to the three forces: electromagnetism, weak, and strong. And this is what we call the standard model of particle physics. It predicts that we have particles that interact via electromagnetism, whose particle associated with it is called the photon. There's the strong interaction, whose particle associated is called the gluon. There's the W and Z bosons that correspond to the weak interaction. There's this famous now Higgs boson that gives mass to particles. And all the particles you know that you're made out of are combinations of up quark, down quark, and electrons. And then there's a partner to the electron that's a type of dark matter we call the electron neutrino. Then there's the two more generations, just heavier copies of the same thing. This is all the stuff, all of the matter, all of the forces and interactions we know in nature, aside from gravity. It's all encapsulated in this one picture of the standard model particle. Here's the mass of these particles. Just to give you an appreciation for the fact that there's these neutrinos that are incredibly light. We actually don't know exactly how massive they are. We know they're less than what's shown here. These are all the stuff you're made out of. Up quarks, down quarks, combined to form protons and neutrons. And then they form neutral atoms with electrons. Then there's these two copies. There's the copy with the charm and strange quark and the muon, and the top and bottom quark and the tau. These are all just heavier copies of up, down, and electron. And then there's these force carrier particles, WZ boson and Higgs boson, that are really massive. And what we keep seeing is that as you get to more and more higher energies, like in particle colliders, you have enough energy through E equals mc squared to produce more massive particles. So you can produce new particles like the top quark, W and Z boson, and Higgs boson, things that we only discovered in the last 20 or 30 years because we had enough energy in these particle colliders to discover these new particles. So there's a question physicists ask, like, what about even heavier particles? What about new forces that could be discovered or that could have been present during the Big Bang when there was enough energy to produce these other kinds of particles and forces. And a big project that relates to this question of what happened very, very early in the universe is called grand unification. This is the hypothesis that at very high energies, like what happened right after the Big Bang, the strong electromagnetic and weak interactions are all part of the same force. They become unified. This is the main thing I want you to understand here is just the word gut. It just stands for grand unified theory. And it's the idea that 3 of the 4 known forces of nature all combine into a single unified force at very high energies, corresponding to what would have happened near the beginning of the Big Bang. So I'm not going to ask you this question, but as an example of what I do want you to know. What does a gut or grand unified theory refer to? It's a theory that unifies the strong force, the electromagnetic and weak force. Okay. Unifies them into one force that would have been apparent right after the Big Bang, very high. Any questions so far? Now, part of the Big Bang theory that gets a little weird is called inflation, which is that there was a period of time right after the Big Bang where the universe expanded very, very rapidly. This is called inflation. Alan Guth in 1981 proposed this to solve 3 main problems. Okay? And so we'll go over these problems, but very, very small time after the Big Bang, like 10 to the minus 36 to 10 to the minus 33 seconds, the proposal is that the universe expanded. So A stands for the size of the universe. The universe expanded exponentially. Okay? Expanded a huge factor, about 10 to the 25. Okay, and this solved a number of problems. One is the flatness problem. Okay, the universe appears to be flat, as we discussed when we talked about the cosmic microwave background. But the universe could have been curved. So why it seems like a coincidence that the universe seems so flat? Well, if the universe expanded a lot, here's as an example, if you're an ant on a balloon and you blow up the balloon, as the balloon expands, so that from the ant's perspective, it looks flatter and flatter and flatter. Right? So if the universe expanded a huge amount, it would look flat, even if it started out curved. Another problem that it helped solve is called the monopole problem, which is that one of the predictions of these grand unified theories we talked about are a type of particle that we don't observe. Well,
What you want?
during the Big Bang, but then the universe expanded so much, you'll dilute all of the monopoles so that, for all intents and purposes, we don't see them because they're so rare. What do we mean by inflation? It's a large exponential meaning very, very fast expansion of the universe that occurred very, very shortly after the Big Bang that helps solve various problems. The technical term is that the universe was trapped in a false vacuum. That's the fancy term to help explain why we think this could have happened. Okay? But I'm not going to go into the technical details about that. But the idea is that when the universe was so hot that there were different forces pulling, those forces caused the universe to expand very, very rapidly. And that explains some of the things we see about the universe, such as the universe being very flat. Now, one of the big questions you might ask once you have studied this enough to understand the universe is expanding, okay? And there are things that control whether that expansion will accelerate or slow down, right? If there's a lot of gravitation, things will try to attract toward each other, and that'll cause the universe to contract. But then there's forces like dark energy that cause the universe to want to expand. So this naturally leads to the question of what is the fate of the universe? Is the universe going to keep expanding the same way it is? Is the expansion going to slow down? Is it going to slow down and then recollapse? Is it going to keep expand more and more rapidly, such that eventually all the atoms in our bodies will be ripped apart? These are the questions that we can attempt to answer. So I'll remind you of this Friedman Robertson Walker cosmology that is the it's a result. I don't know why this color appeared. That's really weird. This is a consequence of Einstein's relativity. It tells you that the rate of expansion of the universe squared is proportional to the energy density in the universe minus a constant k that is +1 if the universe is closed, -1 if the universe is open, or 0 if the universe is flat, times the speed of light squared divided by the size of the universe squared. So depending on the size of the universe, depending on how the energy density of the universe depends on the size of the universe can keep, the expansion rate, h, can change. Here's the kind of main ingredients that go into this. So here's, again, a copy of this equation. And the size of the universe, A, one thing that you can think about that you can probably reason through yourself is that if you have a bunch of matter in the universe, but the universe keeps expanding, well, then the energy density in all of that mass is going to go down, right? If you have a fixed amount of mass, but the universe keeps getting bigger, then there's less mass per unit volume. So if you're in a universe that's expanding, this energy density is going to keep going down. Okay, but if you have energy in the fabric of space-time itself, that's called dark energy, and that's what's shown in green, no matter how big the universe is, the amount of energy density is constant, because if the universe expands, you're just adding more energy per patch of space that you keep creating, because there's energy in the space itself. So that's why there's these two competitions, that as the universe grows in size, dark energy has the opportunity, well, the effect of dark energy remains the same, while the effect of all the matter in the universe that's trying to hold the universe close again is getting less and less effective. Okay, we can kind of plug in, to give you a sense for what this means by creating a few imaginary universes, one that only includes, say, matter in it, one that only includes, say, light in it, one that's just totally empty, and one that only has dark energy in it. And you see that they do different things. Okay, if you have a universe that with only matter in it, it can start off expanding, but that matter will cause the universe to slowly decelerate. The same is true of radiation. If you have a universe with nothing in it, it just coasts, as shown in red. It just keeps expanding, but neither accelerates or slows down. So if you have a universe with only dark energy, that just wants to keep it expanding. The universe just keeps growing, expanding faster and faster and faster. The reality is that the universe is some mixture of all of these. We have dark energy, we have some matter, we have some radiation, right? So the question is, how much dark energy is there? How much matter? How much radiation is there? And that'll tell us whether the universe is slowing down or whether it's accelerating. Right, so these are the possible alternatives. If you have a universe with enough stuff in it, it can actually pull the universe back closed again. The universe can recollapse. That's a universe also without a whole lot of dark energy. So the universe doesn't have a lot of dark energy to push it to expand. Instead, all the matter in it keeps gravitating until it just recollapses. And so maybe 14 billion years from now, the universe will recollapse back in on itself. You can have universes that just kind of coast, that never, that maybe keep growing a little bit, but keep looking very similar. Or you can have an accelerating universe where all the galaxies not only are moving away from each other, but they're going to, over time, they're going to move away faster and faster and faster, such that eventually if we look out at the sky, we won't see any galaxies because they'll be moving so fast away from us, they'll just disappear. And we can look, for example, at data from faraway galaxies, primarily using supernovas, to determine, going back in time, right? As you get closer and closer to the Big Bang, you can look at different speeds, right? So you can actually map out how quickly the universe has been expanding over time. And shown in red is an example of what we expect to see if you have a universe that is going to recollapse. If you have a universe that is just going to coast, is shown in blue. If you have a universe that's accelerating, is shown in yellow. In fact, that is what the data match. Okay, so here's all of our data, and it falls along this line of a universe that's accelerating. So what we see is that the universe is this type of universe. That is trillions of years from now. If you looked out at the sky with a telescope, you would not see any galaxies because they all would have moved far away from us, so we could never see them. In fact, eventually, our solar system would even break apart because the universe would be expanding so rapidly that it'll kind of rip everything apart. If we put everything together, our data from supernova, like I just showed you, also the cosmic microwave background data, it tells us how much dark energy and dark matter there is. The full picture is, these are all the options, including a universe that's curved and open, or including a universe that's curved and closed. Turns out the universe is flat. Okay, so we are on this red line corresponding to a flat universe. And then we could have a universe that recollapses. We could have a universe that expands forever, or a universe that is accelerating and expanding forever. And we are here. We're this black box. Turns out we're, as far best we can tell, we are a flat universe that is expanding and accelerating. Yeah, so here's just one of the plots that are shown at conferences showing various, so SN stands for supernova, CMB stands for cosmic microwave background, BAO stands for baryon acoustic oscillations, which is something very similar to cosmic microwave background. And the intersection of all of this data very clearly gives us a point that corresponds to this point. Big Bang nucleosynthesis and all of these things we've been discussing. And then there's dark energy. This is the observation that the universe is accelerating. The fact that the universe appears to be accelerating tells us that there must be dark energy. That is energy in the fabric of space itself. We don't understand the origin of that energy. That's just an unknown. It's an unsolved problem in physics. Okay. The last thing I want to talk about today is called baryogenesis, which is, if you, I don't think I've told you much about this, but in the Big Bang, you created matter from energy. Okay? The Big Bang was hot and dense, right? And you used E equals mc squared. Energy and mass can be transferred between each other to create matter. Right? This is what we do in particle accelerators. We collide things with a lot of energy, and what spits out is matter, right? Because we've turned energy into matter. That's what happened during the Big Bang. That's why all this matter is here, with all of this energy through E equals mc squared. But there's a conundrum, which is that whenever we do this, we create equal parts of what's called matter and antimatter. And these things actually recombine to produce light. So you combine energy through colliding two particles, you create mass, particle, antiparticle, then they just recombine and form light. So the question is, why? How did any matter actually come out of the Big Bang at all? It should have all recombined and annihilated with itself. We call this baryon asymmetry. That is, somehow there has to be some reason why early in the universe, for every 10 billion particles of antimatter, apparently there were 10 billion plus 1 particles of matter, such that after they all annihilated, for every 10 billion particles, there was 1 left over that could form us, that are made out of matter, not antimatter. So the question is, where did that extra matter particle come from? And this gets again into heady stuff. But the question of how you can get matter-antimatter asymmetry in the early universe is something that goes back to the start of some of these symmetries we're talking about. They have to do with some very, very deep concepts in physics. In physics, there are a couple kinds of symmetries where you can think of like the mirror of something. Literally, looking at a mirror image of something is called parity in physics. And it turns out that there is, well, let me first say there's another type of mirror symmetry called time reversal, right? You can imagine reversing time. And it turns out that in physics, if you reverse time, the laws of physics are the same. Okay? You watch a cannonball go backward in time, it follows the same laws of physics as a cannonball going forward in time. It turns out if you imagine the mirror image of something going backward in time, that's the same thing as an antiparticle. Okay? So there's this deep relation. It's called CPT symmetry, charge parity time reversal. Charge is what is used to refer to if you swap the charge of something, you're changing the particle to the antiparticle. So it's this deep sense. Whereas if you take a particle going backward in time, that, for example, is the same thing as the mirror image of an antiparticle going forward in time. And this is a symmetry that tells us that there shouldn't be any asymmetry between matter and antimatter in the early universe because they're fundamentally the same. Matter and antimatter are exactly the same as long as you imagine the mirror image going backward in time. I know this is kind of heady stuff, but the amazing thing is actually turns out that a part of the symmetry called CP symmetry is broken. Okay, so there's something in the laws of physics that don't respect the symmetry exactly. It could be the origin of what we call baryogenesis. And this goes back to kind of a deep, kind of like a philosophical question you might have, which is that suppose we were able to contact an alien civilization, say through a telephone, and we could talk to them, and we can tell them all sorts of interesting things, and communicate about our lives, send them some music and stuff, right? But if you think about it, there's actually no way of communicating to them what the difference is between left and right. Okay? This has to do with parity, mirror image. If you start talking about, oh yeah, just take your left hand, and they say, wait, what's my left hand? And you say, oh, well, just turn your head to the left. And they're like, wait, but what's left? If you think about it, there's no way that you can communicate for them to look left. You know, for all you know, they could be looking right, only now. This is due to parity symmetry. But it turns out that there's a very specific experiment we could do that could allow us to communicate this to aliens. We would tell the aliens, put a cobalt-60 nucleus in a magnetic field, like shown here. And the mirror image of this is a coil going in the opposite direction, which causes the magnetic field to reverse. And what we see is that when we put this radioactive cobalt-60 in this situation, when it decays, electrons tend to preferentially be emitted in one direction that is different from the mirror symmetric version. And so it actually turns out that there is a very technical way you could tell aliens, oh, well, what's the left direction? Well, make a coil like so, put some cobalt-60 atoms in this coil, and the direction that the electrons are emitted, that's left. So you actually could tell aliens what the difference between left and right is. And it turns out that this is an example. This violation of this parity symmetry is an example of the sort of thing that can cause an asymmetry between matter and antimatter early in the universe. This particular example doesn't do enough to produce enough asymmetry. So physicists, this is this major problem in physics to continue to search for ways in which early in the universe, somehow there's a difference between matter and its mirror image, or somehow there's a difference between particles going forward in time or backward in time, or between matter and antimatter. This has to do with CP and T, charge, parity, and time reversal symmetry. Okay, I know this lecture was full of kind of heady stuff. I'm trying to just give a sense for the beauty of what lies beyond some of the stuff if you ever did choose to study it in more detail. I don't think I have, yeah, I think that's it for the day. Is that, going forward, we're going to delve into some more of the stuff, for example, dark matter. Any questions before I let you go? All right. Good weekend. See you next week.
Thank you. Have a good weekend. Thank you.